So why? The question is why, and the other question I want to answer is what's Rascal for and is it useful? And then the final conclusion you have to run away with is, so okay, so what? Maybe it's useful for you, but this is also useful for me. So what's the why? So what you see in this picture is a picture by Raphael of the School of Athens. I'm going philosophical on you now, right? So this is, pay attention. This is Raphael's picture of the School of Athens. You see academia as it is, people lying on the ground, people bored stiff, people doing nothing, eating. But in the middle are two people having an interesting discussion. And they are Plato and Aristotle. Aristotle being the student of Plato before, but now has become his equal, and they're having an important discussion of philosophy. And the question is, should science progress in a Platonic way? Should we go for the nice ideas, right? Describe what ideas are in their abstract conceptual reality? So is reality abstract? Or, as Aristotle says, no, science can only progress by looking around us and looking at the reality of what we're living in, observing and abstracting from our observations towards the truth. And this is a very, very interesting discussion that's still very, very lively today here at CWI, because half of this institute is doing formal mathematics and formal computer science, informatica, and they are basically the Platonic people, right? And the other half is interested in application and observing whether tools that we develop actually work, if theories when applied in reality actually work. And I think if you are any kind of serious about progress in fundamental research, you have to consider them both. Right? And even though CWI is a fundamental research institute, or a research institute that does fundamental research questions, it doesn't mean that it cannot do the Aristotle way. Actually, it should also look at the Aristotle way of doing research. And the basic, I mean, you can see that the weak points of the one are the strong points of the other way around. So the question is, why were they so anonymous? They really had big fights in the School of Athens. Plato thought he was a traitor. So the other fundamental point here to make here is that if you do not have tools in the middle between research and application, communication is very hard. And the other way is that the tools provide a way to communicate. So here is an example in medicine where you see, you see a picture of science, you know, as the thinker over there. But the idea is that what's that word for is it a magnifier? What's the
microscope?
The microscope, exactly. The microscope in the middle is the way that scientists used to use to discover new things about biology and cells. So that's a nice tool produced by science for science. Now microscopes are used to do to look at the blood of a certain individual and to see if he's sick or she's sick. Right? So the tool is both a tool for science and a tool for application. And by doing many, many observations using the tool on many, many patients, you actually get feedback into science, the Aristotle way. So the tools are a sort of central point here, and they really make the whole cycle of research and application stronger. And we believe that if you do not produce a tool, then it's very hard to communicate with your clients, basically the companies that we want to transfer knowledge to. If we do not show them how it works, but just write academic papers and say, see, it works because it's in the paper. Nobody believes that, right? Because there's a whole kind of trust system that's going on inside of academia that believes results in papers are true, but that trust does not transfer to industry in any kind of way. Right? They see us as the ivory tower kind of people that come up with beautiful ideas but have never been tested in practice. Even though there's formal proofs in the papers that it actually does work, they still do not believe it, and they're probably right. So, and the tools are a way to communicate this more effectively. So now there's one other thing, which is the verifiability. So suppose I make a theory and then make a tool, and the tool does not work, then academia itself will start hitting it on its ass. Right? So it's verifiable theories. That's very nice. And the other thing is, so verifiable means something different than proven. proven is, I've showed that it worked in this way, but verifiable is it doesn't break in another context. Now, transferable I already talked to you about, but these are all pretty boring things. The most interesting thing about academia producing open source is we get the freedom to do anything we want. Right? So we always do the newest thing. That's all what we can publish about. So we can take risks that that companies in the industry cannot take. And we do that all the time. Right? We take risks, huge risks, investing in projects that may be total crap. And that's the 89% of crap you find on the web, which gives you a bad impression about academic open source projects. But the idea is that we can do that and are allowed to do that because the taxpayers give us this freedom. And the 2% that remains, that's the interesting 2% for the industry. So, and that 2% is guaranteed to be very innovative. So, bored? Nobody asleep yet? Okay. That's basically why. And is there any questions about this? I mean, does that ring a bell, or do you still not trust me? Or if anybody has experience with open source projects from academia that failed completely? Anybody started open source projects that failed completely? Are they a success? Who started from academia? There.
So Python started here as an open source project, and
exactly.
You can't say that that's failed.
It has succeeded, very much so.
Mind you, no thanks to CWI.
No thanks to CWI. No. Maybe, I mean,
maybe a bit thanks.
Maybe a bit thanks to CWI. And I'm very proud actually that Python is, sort of started here. That gives us a feeling of pride at CWI. And same goes for MonetDB, name another small stuff that comes here. So if something comes out of CWI that is actually used, we are all extremely proud of that. And in the back, I saw some academics that became entrepreneurs. Yes.
No. Yeah, and back to academics.
Okay. Right. Well, let's continue. So now, what is Rascal? So just I know this is not necessary here, but it's going on YouTube. So I just want to imagine a world without software. And I think from our current perspective, it's pretty handy. Right? So our lives are being influenced by software very, very much. And it's difficult to say because you see the hardware, right? There's no picture of software in here, but you see the hardware, but what's inside is software. And Intel was very, very smart because they have this slogan, Intel inside, right? They have the same problem. The chip is somewhere in this very nice package, but you don't see it. And they came up with the slogan, Intel inside. And they've succeeded in convincing us that it was Intel that was driving all this technology that we needed. And actually, we should do that again for software, because software inside, for real, all these machines do not work without software. And they influence our daily lives. So, okay, you're all convinced of that. But what is it, this software? This is really a key point of Rascal, is what is the problem with software and what is the solution? And I think that in this case you should think of Kafka, right? Kafka wrote books about the enormous complexity of administrative systems and how they can lead people to do bizarre things like execute a man. That's innocent. Now this is what happens with software. It's so enormously complex that nobody understands it anymore. And this word Kafkaesque, which means marked by a senseless, disorienting, often menacing complexity. Right? That's the definition of Kafkaesque. That's my feeling I want to put in your heads when you think about software. And if you've seen any real software, not the software that you wrote, right? I mean, that's beautiful, nice, elegant, whatever. But if you see software of a bank or insurance company or an arbitrary hardware company in the Netherlands that's really big, you see that it's problematic. And what's the main cause of this? One of the causes is size. And here you see, I just wanted to, size matters. Here's a picture of the Pope. He's our champion Bible reader, right? The world champion in Bible reading. The Bible, the Gutenberg version of it, has 12,000 pages. 40-line columns, 3 words per line. It takes some time to read, but nobody really understands it except the Pope, right? So that's kind of big, and nobody understands it. Now this is what a bank in the Netherlands looks like. Like a bank in the Netherlands has 750 million single column pages of COBOL code, unfortunately. If you print it out, it goes a few times around the world. If you try to read it, it takes 1427 years, approximately. So that's sort of the kind of complexity that you have. So it's huge. Nothing interesting in this bank is going on except rent calculations and keeping the addresses of people such that they can send them bills. Right? So there's a lot of complexity here which is not rocket science, so to say. It's just a lot. It's wide, it's not deep. This is the source code of LS. Who knows LS? Who does not know LS? So LS is, if you know Windows, DOS, before you type there and you get a list of files that's in a folder. So that's the command. It's the simplest command that there is in Unix. It's basically the first command you type in when you get access to a console prompt. It's the simplest program, right? Now this is, did it scroll by?
No.
Oh, okay. So this is it. This is the source code of LS. But that's the simplest thing. So what's the reason that LS is so complex? Philosophically speaking, is because we want it to be that complex. It has all kinds of nuts and bolts and bells and whistles, because it has to order the files from A to Z, but then from Z to A. Then it has to put some colorings on special kind of files. All kinds of different features that we want in there. That's why the bank is complex. Right? The bank is complex because every time the bank managers decide they want to sell their product in a different way, they have a different product and the code has to change with it. And COBOL does not have the facilities to deal with that kind of variation points. So COBOL is big because we want it to be big. The COBOL bank is big because we want it to be big. It's not anything in the technology that makes it hard or to make things simple. It's just us. And this is important insight, I think. That has nothing to do with Rascal, that I just want to put in your heads. It's not our fault, it's your fault, right? It's a feature creep, basically, that runs around and wants more features. Still, so if you talk about quality of software, then the most important quality that you can have for software is that it is simple. Software needs to be simple. Quality is a pretty hard to define thing, and simplicity also is, but this is the real focus of Rascal research and the Rascal tool. We want to know how to get better software by making it simpler.
I know two meanings of the word simple, and I don't know which one you mean. So, scissors are simpler than a lawnmower, but I wouldn't want to cut my lawn with scissors, and so it's simpler to cut the lawn than with a lawnmower.
Yes.
So, do you mean simpler in use or simpler in implementation?
I think I mean simpler in implementation initially.
Okay.
So, what I want to know is, what is the quality of this software in terms of its implementation? And what is the quality of this software, what could it be if it were implemented simpler? And I think that the kind of complexity that we have now, for example in the COBOL bank, prohibits the designers of that system to make it actually simpler in its use. Right? Because it's so complex they cannot actually change it to make it simpler in its use. So first, complexity in its implementation, and that should facilitate complexity or simplicity in its use. So I'm focusing on simple here. So the question is, you see these markers here. So TÜV is a brand for quality control. KEMA is also one, TNO is also one, but we do not have these quality metrics for source code or for software. And we do not know when something is simple, we don't know when it's complex, we don't know when it's broken, because we do not have a frame of reference for source code. It's not like a bridge, if it collapses then it's wrong. But software does never collapses, it just keeps on running and running forever, making our lives complex. So now this is the solution of Rascal, and it's a very generic solution that's not by Rascal, it's just the way people do things. It's just you analyze first, you extract knowledge out of a big ball of mud, basically the source code of the system. You put it, and then you get data, which is something different than source code, but it's data. You analyze that, and then you produce more simple representations of the same code. Either a new implementation that's better and simpler because now it's organized, or graphs and statements about the system. For example, let's say I want to know if a system uses that and that database at all, or is that dependency. But that's a question you might have about the system. If you go browsing through all the COBOL code, you know, it's never gonna, and maybe you find a dependency there, but it's actually dead code. So the question is, if it's a very hard question to ask, a very wide question to ask, does this system use that database? It's not so deep, but very wide. And those kinds of questions are the first questions that you can attack by using Rascal. So that's knowledge generating about the code. But what you can also do is simplify the code. So do a very, very interesting, complicated analysis that somebody would write a PhD thesis about. That actually takes your software and puts it in a simpler form that's easier to understand. Such that you can see, aha, this is the part that used to communicate with the user. We're going to take it out and put a web front end back in. But that's not really possible without a very deep and very wide analysis about all the dependencies in the code. That's what Rascal is for too. So what are the challenges that Rascal has to face here? And I'm going to be very generic about this. And if you have technical questions, please just go to me after the talk because they're not in here. The problem here is diversity. Right? So I can make a system that works on COBOL, and I work on that for 3 years, and then it's done. But then the next system comes along, it's written in C, or a dialect of C, or a dialect of COBOL, or a unique combination of two languages. So there is no solution that will, for a specific language, that will live longer than the application to one single company. Basically, we've seen this in practice. We have almost 20 years of experience of applying our technology to companies in the Netherlands and in Europe. It's always different. So the challenge here is diversity. Programming languages, libraries, systems, frameworks, domains. You know, it's quite different to work in a domain like the Department of Defense than it is to work in an insurance company. And you see that the kind of analysis that these people use and kind of precision or speed they use are different. So that diversity that you get when you look at all the Smurfs, basically, and the Smurfs actually are simple, right? So the Smurfs are simple because they're all blue and they all have white heads and just have different attributes, right? So there's a very clear variation point here. But in software, it's quite different. I mean, I should put the Smurfs and put Barbapapa and all of these comical characters in there, and that's the kind of diversity that we're talking about. Right? They're all different, incomparable. It's just that they happen to be drawn on software. So we have all the comic cartoon characters in the world here, and we have to deal with all of this variation. The second challenge is that Rascal has to be multidisciplinary. So analysis and transformation of software systems is a complicated field, and I've lost the but thank you for being there while it lasted. The thing is that what you need to be able to know, what you need to know about computer science is very wide as well. You need to know about math, about programming languages, the specific semantics of these programming languages, about static analysis, about statistics. And that's one of my weak points, for example. I don't know squat about statistics. And this is a weak point in the Rascal group that we have to fill up by getting people that have more experience in there. Because we want to put all of that knowledge that you need to do analysis of large systems into Rascal, such that other people do not have to start and learn all of this before they can do an interesting analysis. By the way, this is Parnassus, also by Raphael, and he shows it's the muses, it's the home of the muses. Right? A multidisciplinary, one plays the lute, the other plays the piano. Oh, that didn't exist yet. The piano, the other part is good at that. A lot of different muses have to be put into Rascal before it actually works and does something. And the final challenge is that it should be fast, but that's impossible because any kind of analysis you do with Rascal is in principle undecidable. Any interesting thing you cannot compute for real. So you want to know whether your program always terminates, impossible to compute. You want to know if there's any dead code, and just point at the dead code user you can remove so that the system is smaller. Impossible to compute. So
impossible in general.
Impossible in general, exactly.
But not in particular.
But not in particular. So so you get a trade-off there. So how particular are you willing to get? And you want to be as wide as possible, but the wider you get, the slower the analysis becomes, because it has to be more precise and more precise, and it's getting towards that it will never terminate. Right? So it's getting more and more complicated to get a precise result, and it's the exact what I want to convey with these images of the bow and arrow and the atom bomb is, if you design something like Rascal, it should allow the use of both a bow and arrow and the atom bomb, because we want, for certain analyses, we want to be very, very precise, because we want to know, does this program terminate? And then we can also choose for a very specific solution. Or we want to give, put online a tool that approves termination for a lot of programs, right? But then it will be, and it would be, that would be a very fast program, but it would be rather imprecise. For example, it would say, well, maybe it terminates, or it does. If I can prove that it terminates, then I will terminate. But if I cannot prove it, then I will just continue on forever and ever. So there's trade-offs there. And if Rascal would fix the trade-off at a certain point, then it would be useless, because it would lose this whole scope and this whole balancing trick. It would be only useful for those kind of people, not for the others. And this is our major research challenge, actually, to make a system that has a variation point in the precision efficiency trade-off. That's very hard to generalize, very hard to design. What it is a programming language. So now you've been waiting for that, of course. So what is this Rascal abstract baby? Well, it is a language, and it's specialized exactly only for source code analysis and transformation. It doesn't do anything else but that. Of course, you could write an operating system in it, because it's a programming language, but I guarantee you it would be a bad operating system. So it would analyze the bits and then transform them and then think about it again. And then so this is a language that has specific features that are very, very apt for program analysis and transformation, nothing else. So the ingredients are, I want to emphasize that our group, if we add up all the experience, we get over 50 years of experience in software analysis and transformation. So, and this is sort of Paul Clint, who is my PhD supervisor, is at the end of his career, or at the beginning of his next career, depending on how you look at it. But all of his experience is in there for sure. All my experience, which is about 10 years, is in there. And what we did is we studied our own previous versions of the systems and all of our competitors for about 2.5 years, in depth, talked to all our competitors, the other academics that are in this field, and we tried to come up with a system that would integrate all of this knowledge into one. This was a very hard and long job. And so then you know what you need. Yes?
Did you study the Rebel language?
Rebel?
Yeah?
I don't think so. No.
Interesting.
So I missed that, huh?
Yeah. Actually, Rascal is a lot like it.
It is? Cool. So we're on the right track with that. Maybe we can join forces then. Are you a Rebel author? Or?
No, I'm not the author.
Okay.
I'm going to present an open source halfway clone of it.
That sounds good.
After you.
Okay. I'm sitting in. So one of the things we learned from all of these other systems is that they tend to look very complex. So from a user point of view. So like they have program transformation systems based on term rewriting. And term rewriting in itself is an elegant and nice concept for transformation. You can do pattern matching and substitution. If you look at a program analysis system written as a set of term rewriting rules, nobody understands them. For real. They are really simple, but they are too academic. Well, all these systems do, term rewriting systems do, is decide when to apply certain substitution. Right? Take this pattern of go-tos and replace it by this while loop, for example. As a rewrite rule, or as a collection of rewrite rules, it looks very academic. But all it's really doing is if then else and substitution. So we decided to get rid of that and say, okay, what are the basic concepts of these rewrite rules that everybody in academia is using for program transformation, and explain them in a way that a normal programmer would. So Rascal has if then else instead of rewrite rules, because that just flies better with people that program all the time. It does no real conceptual difference. It's just a conditional match or don't match. And it's an insight that, so you have to let go of sort of your heritage. I was brought up in the heritage of algebraic specification, and now I have to let go of my equations. But it makes it all the more interesting and easier for other people to play around with. It's like algebraic specification inside. You don't see it, but it's still there. The second thing is integration. So that's what Rascal is, I think, pretty unique, except for that language that we just heard about, maybe, is that it takes two fields that are traditionally different, which is analysis and transformation, and tries to fuse them together as much as possible. I'm not going into details there, but we think that their Rascal is pretty unique. And of course, the expressivity is what every language claims. In this language, you can express yourself more efficient than in others, because we are more domain specific. And expressivity is a claim you should make. If it's not if it's not easier to program your solution in this language than it is in Java or C, then why does it exist? Right? So shorter programs. That does not mean that there are easier programs to write. And so an analysis, every analysis requires thought, and intellectual property is created when you write a Rascal program, even though it's just one line. Right? It's very important to think about what you write. Even though it's short, it may have taken weeks for you to come up with. So Rascal does not solve that problem for you, for real. Right? What it solves for you is that you can experiment with different kinds of analyses, different kinds of transformations in an expressive way. But it doesn't, that's a Dutchism, I'm not going to say that. It doesn't, you're not free of having to think. Basically, that's so it's free. You're free to use Rascal, but you still have to think for yourself. This is a kind of simplest Rascal program that we have that produces something usable. So one of the ideas of Rascal is should scale down to things that we're not interested in. So, like, we don't write papers about systems that just go through the file systems of the bank, check out the extensions of the file, and make a pie chart out of that. But that's what managers are interested in, right? So if Rascal should start with the simplest things, then slowly users can try and use it for more complicated things. This is a Rascal program that you write to do that at the Dutch tax office. And people actually did that, and they were very, very happy to get this insight. So this is, it applied to some Java, piece of Java code. And you see, for example, hey, I thought my project was Java, but in the end it appears to be mostly XML, which is weird, right? So most of the files in this project are actually XML. So this very, very simple analysis, you write in, let's say, 5 lines of Rascal code, and it also produces the pie chart for you. So the integration with visualization and fact extraction, analysis and visualization here in 4 lines of code. Don't try to understand it, because I had to explain too much. But I would just want to, convey the idea of 4 lines of code that does something simple, as opposed to a term writing system with 3 lines of code that do something untractable that you really cannot understand. Now here you just see a program that has a beginning, a middle, and an end, and it will work. This is another example. Here it's a bit bigger, because here we are designing a very specific visualization for a question, which is where in my system are classes that are very complex, or more complex than they should be. So in general, it's a well-known result in program understanding that methods in classes should be short. About 10 lines is understandable for most people. When it gets bigger, it gets exponentially harder to understand the method. So what you want to know is, are there any classes which are in principle very big but have few methods? So here what I've done here is I've plotted the number of fields on the y-axis and the number of methods on the x-axis. And the color of the box is more red when it contains more lines in total. So you see a very small box there in the middle, which is red, which is a humongous class, but it has few methods and few fields. So some COBOL programmer has started programming Java, right, and wrote a main or something with kilometers or something like that. But to find that needle in the haystack, I've designed this visualization, and it takes about a page of code. Right, it's a completely new visualization.
When you say it's exponentially harder, is that rhetorical, or do you have evidence that it's exponential?
No, most of this talk is rhetorical, by the way.
Because I think it's quadratic, not exponential.
No, it's not even quadratic. We don't know.
Oh, well, I think
Yeah.
I have evidence of contrast.
Okay, but they make it, I mean, people that have, read methods that are longer than 10 lines make a lot more mistakes.
Yeah, and I think that's
Yeah,
contrast.
it's quadratic.
I think I have some evidence.
For me, it's exponential personally, but I don't. I'm just a bad programmer. So this is a nice point, right? So what you see here is a very dense code. Every line means something important. It's not like when you program in Java, where you just write lines and it goes on and goes on and on and does nothing. And so it's very dense. Like Python, for example, you can write very dense code. That doesn't mean it's bad code. It means that it's easy to change for the guy who wrote it, to change it to do something different. So that's the essence of Rascal. You get dense code, but it's very nice to change, very nice to experiment with. I could make a different visualization that in a few minutes. It does, maybe uses the color for the lines of, for the number of methods, or one that draws circles, or make a 3D diagram with these metrics. Now, so what? This is the so what part. Do you have to download Rascal if you're an open source project and you need to get insight into quality? Do you need to write Rascal scripts now? Can I get benefit from it now? And the answer is no. So Rascal is in its incubation stage. So maybe its logo should have been Calimero instead of this very aggressive wasp that we have. It is right now. It really is a proof of concept. But the intention is, like with our previous system, the ASF SDF meta environment, to at least go on with this for another 10 years. So we have a plan for Rascal that projects out for 10 years of research and education in industry in the Netherlands. So that's what we want to do, but it's not there yet. We are in the first phase. We have taught it at the University of Amsterdam, so there's about 100 people that know how to program in it. That gave us a lot of feedback. We have applied it in several industrial applications, but very, very small master thesis projects. And we're getting feedback from that. So we're trying to simplify, because in many places it's still too complicated. So we're trying to eat our own dog food there. So we want it actually to be simple. If you are an industrialist or an open source project and you are interested in seeing how this flies, then try and interest one of our master students at the Master Software Engineering for it via me, and we can get a project running up if you want. So that's like, and you get a free, basically free consultant, does something very technical. This guy is not going to be a consultant in the sense of the word. He's going to actually take your source code and do something useful with it, or girl. But we yet have to get a girl at the Master Software Engineering, which is kind of weird, I think, because software engineering in itself is a very wide, interesting, multi-paradigm subject. So I think girls should definitely be interested more in this field. So the next step is really we're working hard on improvement, and if you are willing to give us cases, then we would be happy to try.
Have you tried it on itself?
Yes, we actually right now we're rewriting it, transforming it from using lots of the visitor design pattern to interpreter design pattern, because it's faster. So why is Rascal free? By the way, this is the Shawshank Redemption, and that guy has just crawled through 300 meters of mud, or shit, to be free. And the other guy is the guy looking at the hole on the other side, right? That's, maybe you've seen the movie. But it's free because as scientists, as researchers, we open ourselves to the scrutiny of the crowd. Right? We want to be judged. That's by ourselves as a community of researchers, but also by industry. And it's free because we hope that it's useful for people. We don't want to put any limitations or walls between what we produce and the people that use it. We are paid by the government, basically, so this software is for everybody in the world. It's BSD4 licensed, or Eclipse public license. What this license says is exactly what we don't want to project, right? It says, well, you can use this software, but it's not good for anything, right? That's what these open source licenses say. And I think that's one of the key points also in the difference between America and Europe, is in America they actually read the license, right? They see open source and they read, this is software, but it's not good for anything. and the people who wrote it are not liable for anything. Now what, right? In Europe, it's free, go and use it. Now, this is a real difference, and that liability issue is important, because what it actually says, if you download Rascal, it says you have to take an active part in it for you to be useful, right? We cannot guarantee for you that you can use it without our help, and without you paying for our help, or without you investing time and money for understanding what Rascal does and how to use it. So that's not, the license doesn't say that. Well, it sort of says that. It says not good for anything, but it doesn't say what you have to do for it to be good for anything. You have to invest in it. So invest in time to host a student from us that will teach you how Rascal can be useful for you. That's my answer to that question, and to the basically the big hole that should be at the end of every open source license. So basically the so what license. So now what? So, and I also want to thank other open source software in particular, because we build on others' open source software. We cannot build on GPL software, because that disallows companies in the Netherlands to actually use it. And SAP, and IBM, and Microsoft have all used our software after we put it to BSD license. So, as government-funded research scientist, I cannot really use the GPL, although personally I like it a lot.
Sorry, I don't understand that. What's the problem?
The companies do not want anything, any license that rhymes with GPL, LGPL or whatever, inside their company for liability issues. So I had to change the license again and again, so now we stick with BSD4 and GPL. But I want to thank Eclipse.org, and if you all use Eclipse.org, I think a round of applause would be in order. You know, a humongous open source project, thousands of people working together, producing something useful. Pretty impressive. Thank you very much. If there's any questions. Of course. Yes. Jeff.
Yeah. I was wondering, why have you invented a new language instead of a set of modules for Python or Prolog or whatever?
The fun answer is we always design new languages in our group. So, so that's just our hammer, and the nail was just lying around. But the real reason is that the languages we've seen that are specialized in transformation and analysis produce a lot faster and more scalable implementation. So the library solutions we have do not scale beyond toy projects. For special, you cannot specialize, optimize. So the compiler allows you to specialize. The other is documentation. So the language, its syntax itself, makes it easier to read and stuff. But you could do that as an embedded DSL.
Okay, but you're actually compiling the language, so you have a bytecode that is specifically optimized to the problem at hand.
That's our plan. Our previous, ACE of SDF would do that. The previous implementation is an interpreter so that we can still change the language pretty easily. But the next version is there's now a postdoc specialized in bytecode compilation. We will focus on that. I saw another hand. No, that was you? Fake hand. Oh, 5 minutes. Well, I can fill up 5 minutes if you want, but you can also have a cup of coffee and talk. Thank you very much.